Thank you, Eric. Good afternoon, everyone. And first of all, thank you to the organizers for inviting me. It's been a real pleasure being here in India. So today I'm going to talk about Hausdorff dimensions of pro-P groups. And Uri gave a really nice and extensive introduction to pro-P groups last week, and also more generally to pro-finite groups. So I think I can get away without defining it. Also, lots of people have spoken about it yesterday and today. So I will define it, recall the definition when time comes. But for now, let me begin by just telling you a bit about this concept of Hausdorff dimension. So it was invented, I suppose, by Felix Hausdorff in around the 1920s. And what it is a generalization of our usual concept of integer dimension. So we all know what we mean by something of dimension 1, like a line, dimension 2, a square, dimension 3, a cube, and so on. So Hausdorff dimension is one generalization of integer dimension to non-integer dimension. So it can take non-negative values. It's not the only generalization of integer dimension. There are others like the Minkowski dimension, the box dimension, and some others, but this is the one I want to talk about today. Maybe I should say, so initially it was invented around the 1920s, and from that time on, it was mostly applied to fractals and shapes in nature. So that's kind of how its story started. And what is a fractal? So a fractal is an irregular shape such that when you, no matter how much you zoom in onto your fractal, any part of it, it retains its level of irregularity. So you kind of see this, the whole shape again, no matter how much you zoom in. So there are lots of examples of fractals in nature, shapes in nature. For instance, snowflakes are examples of fractals, so they're kind of spiky, and if you zoom in on one of the spikes, it's just a spiky because you see the crystal structure and so on. You do see fractal-like patterns in trees, plants, ferns. Also, certain types of broccoli are also fractals. Coastlines are examples of fractals. But let me give you an example of mathematical fractal, just briefly. This is something that probably a lot of you have encountered before. This example is called the Cantor set. And so the way one would describe it in order to see that it's a fractal is to, I'm not going to write it down because I don't want to talk about fractals, but let me just say how you would view it as a fractal. So you start with the unit interval, and you take out the middle third. You've got two disjoint segments, so that's kind of, you kind of define it recursively. So you first take out the middle third of your unit interval, and then the next stage, you take all your two remaining segments and take out their middle third, and you keep on doing that. So to every remaining segment, you take out the middle third, and you keep on doing that to infinity, and at the end of the day, you'll get a collection of points. So the Hausdorff dimension of the set, if I call the Cantor set C, the Hausdorff dimension, this is the symbol, the notation I will use for Hausdorff dimension of the set. So one can work it out if you know how Hausdorff dimension is defined, which I'm not really going to say, but let me just tell you that it has Hausdorff dimension log 2 over log 3. And so one of the uses of Hausdorff dimensions to fractals back then was that it gives you an indication of how to treat this object that you're considering, because as I said, the Cantor set is just a bunch of points, disjoint points, but it doesn't behave like a finite collection of points because that would just have dimension 0, like a point has dimension 0. So it's a really dense collection of points, and it's reflected in the Hausdorff dimension, which is strictly greater than 0, so it doesn't behave like a finite collection of points, but it has no length, so it's not quite a line. Anyway, that's fractals. I'm not going to define the original definition of Hausdorff dimensions in the context of fractals because we're not going to really need it, but let me just say a bit about how it's defined. So as you can imagine, the examples I've given you are fractals. I said fractals in nature, but mathematically they are subsets in our real dimension or real space. So in other words, we're looking at subsets of metric spaces. So this original definition of Hausdorff dimension is given in terms of metric spaces. So it uses notions such as open sets, open covers, subcovers, and stuff like that. So what I am going to talk about today is an application of Hausdorff dimension to the bit that I erased, so to groups. But we're only really interested in the application of Hausdorff dimension to infinite groups, and I'll say why, not finite groups. So I'll put infinite groups in brackets. But actually, at the moment, we don't have an application of Hausdorff dimension to all infinite groups, just profinite groups, and I'll be talking about pro-p groups. And so there are two hurdles to go from sort of fractals and subsets in real space to groups is, okay, so there are two hurdles. And the smaller of the hurdle is, as I mentioned, that Hausdorff dimension is defined in terms of metric spaces. You need this notion of a distance function. And that's not too much of a problem because there are lots of groups where you can associate a natural distance function, but still that's an issue. But the bigger hurdle is that this concept, this formula, if you will, of Hausdorff dimension is given in terms of open sets and covers, so metric space notions. And that's something that's really unwieldy. And I mean, where do you start if you're dealing with an algebraic object? So that's kind of the biggest problem. If you want to apply it to groups, you need kind of to translate your definition of Hausdorff dimensions. You need an algebraic formula. So this came about, so people succeeded in coming up with an algebraic formula for profinite groups. That's what happened in the 90s. So this was introduced in the 30s, but in the 90s we have an equivalent formula for groups. So let me, first of all, let me not write that down. First, let me tackle, so the two hurdles was, of course, first of all, you need a distance function, and the second is you need a workable formula. Let me say how you would one way of coming up with a distance function is as follows. So before, let me just say that this application is not at the moment to all groups. Maybe that will come about later on, but let's just say not to all groups. All right, before I go into telling you what one can take as a distance function and then giving you the algebraic formula, let me say something about why we don't want to consider finite groups. Okay, why do we not want to consider finite groups? Well, going back to this example here, what did the Hausdorff dimension of the Cantor set actually tell us? This value here. So it told us something about, in some sense, how much space the Cantor set takes up within the units interval. So it's kind of, the Hausdorff dimension is a measure of how dense set that you're considering is in your world. So it's a measure of densities. So in the context of groups, you're interested in measuring how dense a subgroup is of a given group. So densities of subgroups. So why we're not too bothered about finite group? Because we already have a way of measuring density. So I'm only interested in really p groups, and I'll be talking about pro-p groups. So let me say how, if you had a finite group G, a p group, so it has some order, p to the b, and if you have a subgroup of G and H has got some order p to the a, I mean, there are many ways which you could come up with a way of measuring how dense H is in G. You could take maybe just the order of H divided by the order of G, but if you have a very large group, if A and B are very large, then maybe that's not the best way of measuring how dense H is in G. So one way, which is maybe reasonable, is to take log of the order. So you could take log to any base, but of course, I guess if you're talking about p groups, it's more natural to take log to the base p. So yeah, this is quite a decent way of measuring how, for finite groups, how dense H, your subgroup is in your finite group G. So for finite groups, we're happy, so that's why we're going to focus on infinite groups. Okay, so the first hurdle, we need a distance function for our group. So this is done via what's called a filtration series, and that's been mentioned, I think Valerie mentioned that in his talk. It's just a descending chain of normal subgroups. So in order to, we need a distance function. This is how we go about. This is one way of going about it, the distance function. So I'm going to fix a descending chain of normal subgroups, and because I am going to restrict to profinite groups and more generally pro-p groups. Okay, more specifically pro-p groups, I'm dealing with topological groups. So this concept of open and closed, open subgroups and closed subgroups, we have that. So when I say fix a filtration series, I mean a descending chain of open normal subgroups. Fix filtration, a filtration series. Let's call it curly S for my filtration series of G. So G will be a profinite group here. Anyway, so what's a filtration series? So you start with G, and then you have sort of subgroups that are contained in it forever, and you require two conditions. So where all these subgroups are normal and open in G, so the GIs are normal and open in G, and you want their intersection to be trivial. So this is what you require, and once you have this, you can then define a distance function. Of course, so a distance function, what does that tell you? You want to know if you pick two random points in your group, how far are they apart? So let's take two random points for little x and little y in G. This is how I would define my distance function here. So the distance between x and y is, okay, so it's a bit long, but let me write out what it is. So basically, let me tell you first what it is. So how the distance between x and y, so I go down my series bit by bit, and I want to see in which of these groups do I have x is equivalent to y. So x is always equivalent to y mod g. And at some point, because I have this condition here, x will stop being equivalent to y mod gi. So I want to take the maximum I where they are equivalent. And then I take 1 over that index. So g over gi, and the infimum, of course, because I want the maximum I where this happens, where x is equivalent to y mod gi. Okay, so it turns out that this turns my profinite group into a metric space. So that's the first hurdle overcome. Okay, so the second hurdle is that I need an equivalent algebraic formula for the original definition of Hausdorff dimension, which I did not write down, but I said it's in terms of open subcovers and open sets. And so this was given in the 90s via the effort of 3 people, first by Abercrombie in 94. And so it's a formula for the Hausdorff dimension of a subgroup of a profinite group. And because we're dealing with profinite group, topological groups, when I say subgroup, I mean closed subgroup here. Anyway, so it was the effort of these people. And the formula is, of course, the Hausdorff dimension of a subgroup is equal to something. And Abercrombie did one equality, and Iftach Barnea and Barnea-Shaler did the other inequality. So that's why there are 3 people involved. Okay, so what's the formula? So G is a profinite group, and then I want H a closed subgroup of G, and then this is my notation, the Hausdorff dimension of the subgroup H. Before I write that down, let me point out there are 2 differences for Hausdorff dimension of fractals in nature or subsets in the real space compared to Hausdorff dimension in the profinite world. The first difference is here, when you talk about snowflakes or Cantor sets, your world is your real space, your 3-dimensional real space or 2-dimensional real space, and you're interested in computing the Hausdorff dimension of a subset in your real space. Here, your world is your profinite group, which you fix. So if you change your profinite group, you change your world. And so I need to say Hausdorff dimension of my subgroup in G. And here, you can have Hausdorff dimension, you can have subsets with Hausdorff dimension 2, 3, and so on. But in this case, the Hausdorff dimension lies between 0 and 1. Also the way the formula and the rescaling works. Okay, so what's the formula? So bearing in mind we have this kind of natural logarithmic fraction for finite groups, it's going to look similar. So it's as follows. Log the subgroup H, and then you want this GI from your filtration series, this index over log of the index of GI G, and then you want not the normal limit, you want what's called the lower limit, which I'll recall now. But yeah, that's it. Okay, so comma, where, let me remind you what the lower limit of a sequence is. So if I have a sequence AI, the lower limit is, okay, so you look at your sequence and you form a series of subsequences from it. From the first subsequence to the next, you kind of throw out the first term. Okay, so in other words, this. So when I is 1, you look at the original sequence, And when I is 2, you start from A2, A3, and so on, 1. Okay, and then you look at the infimum of the sequence. So you've got a collection of infimums, and then you take the supremum. That's the lower limit, or limits inferior. There's equally an upper limit. But yeah, so this is the lower limit in the formula. Okay, so sure. Oh, in the profinite topology. And yes, so we have a formula, an algebraic formula. But as Frank mentioned in his second talk last week, that sometimes you have these really amazing results, they're very hard to apply. So in this sense, we've got a formula that's brilliant, but often the issue is it's very hard to compute these factors. Because as you can see, you really, okay, so let me give you an example, and this is actually one direction of research in Hausdorff dimension of pro-p groups. So one direction that people take is if you have an explicit pro-finite group, or more commonly people have been working with pro-p groups, if you have an explicit pro-p group G and an explicit subgroup, and you want to compute the Hausdorff dimension of that subgroup in that explicit, H and G are explicit, and maybe even have a presentation for them, but still, it is often very difficult to compute these quotients for more or less all i's. All i's is what you need. And so this is where gap sometimes comes in handy if you have an explicit presentation for H, and if you understand your GIs very well, you can compute these orders for small i's, and then that helps you gain some intuition about what the pattern is. And often for the case of explicit H and explicit G, if you've got, for instance, if you are familiar with the Grigorchov group that acts on an infinite rooted tree, a lot of computations with Hausdorff dimension has been done for subgroups like them. So it's not enough to have an estimate. You often need to really know exactly what's going on. Yeah. Okay, so that's something I was hoping to shove under the carpet. No, it varies a lot. So strictly speaking, I need to put an S for my distance function. And strictly speaking, I need to put an S here. So it does depend on the filtration. And because in some sense, you can really choose loads of filtrations. This condition you can satisfy very easily with lots of possibilities. So in some sense, you can have really wild differences between the Hausdorff dimension of the same subgroup in the same group if you change your filtration series. But luckily, for pro-p groups, let me maybe write it over here. There are 4 standard filtrations to take for an arbitrary pro-p group. And this is kind of the setting that people work in terms of Hausdorff dimension. Anyway, so there is the p-power series, there's the Frattini series, there is the lower p series, and the dimension subgroup series, which Professor Passy has worked a lot on. So that's a dimension subgroup series. So the p-power series, you start with G, and then the next term is defined by taking the subgroup generated by all p to the I powers, for x running through all elements in G. The Frattini, you start with, of course, the original group, and then the next term, you just take the Frattini series of the previous one. I minus 1. And the lower p series, let me just write it down. It's similar to the lower central series, but of course, remember you need that your terms have to be a finite index, they have to be open. So you add an extra, okay, let me just write it down. You take the commutator of the previous term with G. I'll just get lazy and stop writing G's. And also you take the pth power of the previous term. So that's your lower p central series. And this one I won't define because, write down because more or less. But yeah, so these are these 4 natural filtrations, but of course, in some cases, you also have some other congruence filtration as well. If you're looking at pro-p groups like the ones that Uri and Nert spoke about, for instance, if you're looking at the first congruent subgroup of this group, which is a pro-p group, then you would take the congruence filter, which often sometimes coincides with that guy. Yeah, so it does actually depend, but I didn't want to mention, so I'd shove that under the carpet. Yeah, so that's something that Benjamin Klopsch has looked into. If you have filtrations that are kind of close to each other, you have to write that down precisely, then you would get same house of dimensions. So there are some results that say if they are close, it's not a very easy, yeah, if they are close, then you get the same house of dimension. In some cases, you're okay. Sorry, say that again. Because the original definition given by Felix Hausdorff, so that is the definition of house of dimension, and what they showed is that the same definition is equivalent to this algebraic definition in the profinite setting. So it's not a new definition. They really showed that it's the same definition. Yeah, so they did a lot of work translating it from metric spaces to the algebraic. We now have a more workable formula here. Great. Yeah, so that's one line of research where gap comes in handy if you have an explicit H and explicit G. So the other direction so there are more than one, okay, several directions, but the one I want to talk about today, the other direction is you don't deal with an explicit G and an explicit subgroup H. You're more interested in a nice family of pro-P groups. And, whoops, getting ahead of myself. So the other direction of research in this area that I want to speak about is where you restrict to looking at a nice family of pro-P groups for G. And then you're not just interested in one subgroup H, you're interested in all subgroups of your nice G. And you want to look at the collection of all possible house of dimensions that occur when you run through all subgroups. And that is called the Hausdorff spectrum, which I denote like this. The original notation, which was in Iftak Barnea and Barnea-Shaler's paper, was spec of G, which is probably quite confusing. So my collaborators and I prefer that. As we saw in Anher's talk, he also had a spec of G, which was the orders of the torsion units. Yes, so it's something completely different. So we prefer this. And as I said, it's just a collection of all Hausdorff dimensions of subgroups as you run through all subgroups. And of course, because we're in a profinite group, we're only interested in closed subgroups. Okay, so this other direction of research where you don't deal with an explicit G, but a nice family of pro-P groups, the questions that you want to ask is what sort of form this Hausdorff spectrum takes. So of course, we know it's going to be a subset of the unit interval. So the kind of questions you can ask is your Hausdorff spectrum, is it going to be finite? Yes. Yeah, it does. Yeah, good point. Yeah. Actually, everything depends on the filtration series, really. Yeah, so even with the standard ones, often you get these guys behaving similarly, but this one is often the problem child. As you can, maybe if you're happy with the definition of this, which I didn't say, but often the problem is that no matter how far you go down in the terms for this lower P central series, G plays a very strong role. So you always have G, the top G, always influencing what happens lower down. So that often is the problem child. And you can get a very different Hausdorff spectrum. Yeah, so the kind of questions involved, if you look at a nice family of pro-P groups G, do you get a finite spectrum? Do you get a countably infinite spectrum? Or do you get an extremely infinite spectrum with an interval? That kind of question. And so also generally one restricts to finitely generated pro-P groups, because if you have an infinitely generated pro-P group, lots of things can happen. The question really only makes sense if you restrict to finite generated pro-P groups. And that's what we're going to do. Okay, so what's the nice family of pro-P groups that we want to look at? And so this is a very special class of pro-P groups. Special because they've played quite a central role in the theory of pro-P groups, and they're very important. They are kind of a bridge between analytic group theory and more classical profinite group theory, and they've also been used to disprove conjectures in finite P groups, and lots of other things. So these are the p-adic analytic pro-P groups. And generally, one just says p-adic analytic group. You drop the pro-P group. Everyone kind of knows, hopefully, that it's a pro-P group. So you just say p-adic analytic groups. And this is actually something that Uri was hinting at in his lectures last week. He mentioned, if you remember, the terms uniform and saturable groups, and they are basically p-adic analytic groups. So these are analytic, what are they? They are analytic groups. They're also analytic manifolds, Lie groups. There's this whole analytic side to them, which I don't really know so much about, but luckily for me, there's an equivalent group theoretic definition of p-adic analytic. That's very nice and short. So let me define them for you. So a pro-p group is p-adic analytic if in some sense it's reasonably close to being abelian. What does that mean? That's quite vague. Is p-adic analytic if the following one-line condition holds, so if and only if, the rank of G, and I'll tell you what that means, is finite. Where the rank of G is the supremum of all the minimal number. So if you run through all subgroups, closed subgroups in your profinite group G, this is the minimal number of generators. If you look at all the minimal number of generators, whoops, close. Yeah, so if you run through all the subgroups and you take the supremum of this is finite. So in other words, if you're p-adic analytic, you cannot have subgroups, closed subgroups, of course, with which need arbitrarily large generators. You can't have a subgroup which is not finitely generated. With DH subgroup H, with DH arbitrarily large. Let's have a look quickly at some examples, or one example and one non-example. So the most basic pro-p group that we have seen in the last couple of days is the p-adic integers, ZP. So this is abelian, and it is p-adic analytic. What else can I say about this group? It is topologically generated by one element. Also, so this is something maybe you see straight away, but it does require a bit of a proof, which I won't go into, but let me just state it. All non-trivial subgroups are finite index. Finite index here. So with this bit of information, we can more or less write down the Hausdorff spectrum of p-adic integers more or less straight away. But I need to tell you two things first. Okay, so let's go back to the formula for Hausdorff dimension. So just looking at the formula, Hausdorff dimensions here, we can observe two things. Okay, we can observe stuff about the extreme subgroups in your pro-p group. By extreme subgroups, I mean, if you have a closed subgroup that is a finite index, what can we say about the Hausdorff dimension of H? Remember that Hausdorff dimension is a measure of density, so how dense your subgroup is in the big group. So remember, we're dealing with a big infinite pro-p group, and if we have a group that's a finite index, it's basically the whole group. And from the formula, you can also see after a while, if not straight away, that if you have a finite index subgroup, the Hausdorff dimension is 1. So it's the same as the Hausdorff dimension of G. Doesn't matter. This is independent of the filtration. Okay, and then the other extreme case is when your subgroup is very small, when it's finite. And again, from the formula, you get 0. Yeah? The smallest possible. It's like the trivial, essentially like the trivial subgroup. Okay, so with these two things in mind, we then, based on this, we get the trivial possible spectrum to 0 and 1. Non-example of a pro-p group that's not p-adic analytic. In some sense, the smallest pro-p group that's not p-adic analytic is the following. And why is it the smallest? It's because it's 2 generated. So this just means it's called the profinite wreath product, the symbol. And what this means is just simply this, that it is the inverse limit. Remember, a pro-p group is an inverse limit of finite p groups. It's an inverse limit of these wreath products, the standard wreath. So in here, you have the subgroup. If you take the inverse limit of the base groups here, so you get this elementary abelian group, which is infinitely generated, not finitely generated. So that's how you see it's not p-adic analytic. And in terms of Hausdorff spectra, here you do have to restrict to the filtration. So if you restrict to the top filtration, you get the whole interval. And this group was quite special because it was the first example of a finite generated pro-p group, which gave full Hausdorff spectrum. Okay, right. Sorry, geez, this group. Okay, so what I want to do here is say, what results do we have about the Hausdorff spectrum of this special class of p-adic analytic? So this was a result in the same paper by Barnea and Barnea-Shaler from '97. So they studied p-adic analytic groups, and this is what they discovered about their Hausdorff spectrum. P-adic analytic, then, all good? Yes, the p power, sorry, this one, yeah. It's also the same, it's the full interval with respect to f and d, but not here. Yes. Yes, let me write this down, and then I'll answer your question. So what they proved is that this spectrum is very rigid. It's finite. And they also, remember, I didn't really go into it, but a p-adic analytic group, I also said it's an analytic group, it's a Lie group, so it has a dimension as a Lie group. So they showed that the Hausdorff spectrum, it may not take all of these values, but it can't take any values outside this set, where this little d is the dimension as a Lie group. So they showed this, where d is the dimension of this p-adic analytic group as a Lie group. Okay, so, right. I'll come back to your question, Pooja. But okay, so they showed this, and from this result, one of the big open questions in this topic of Hausdorff dimensional pro-p groups arose. So a big open question is the following: does the converse hold? So in other words, what do I mean specifically? If you have G, a finitely generated pro-p group, and it has finite Hausdorff spectrum, so you're not even insisting that the Hausdorff spectrum takes this nice form, as long as it's finite. Does that imply, so this is the question, that if G does it imply that G is p-adic analytic? This is still open. And there's only been one effort towards this, and that's what I'll talk about now. And I'll come back to Pooja's question. So this question was in Barnea and Barnea-Shaler's paper, and there in their paper they only considered this. And then together with Benjamin Klopsch and Amaya Sugadi Reitzabal, we considered the question of what about all the other filtrations that I raised. It was 2019. And then we extended their result for other filtrations, so also F, the Frattini series, and the dimension subgroup series. But L is a problem that we're still working on. We don't even know with respect to the lower P central series, which was the problem child, whether or not, if it's p-adic analytic, whether or not it's even finite. But L is a problem. We're still working on that at the moment. Okay, so there's been just one effort in the direction of answering this question, and that's by us. So let me just shorten this to KCZ. And so the answer is yes, if, of course, G is soluble. So if you're in the setting where you're dealing only with finitely generated soluble pro-P groups, then we have an if and only if. If your group is p-adic analytic, the Hausdorff spectrum is finite. If your Hausdorff, you don't know what the group is apart from the fact that it's finitely generated and soluble. If the Hausdorff spectrum is finite, then it's p-adic analytic. Okay. So let me say a little bit about the proof. It's quite simple in some sense. So what are we trying to show? We want to show that if G is finitely generated, soluble, and the Hausdorff spectrum is finite, then we want to show that this implies that it's p-adic analytic. So we want to show this implication. Easier to work with the negations. Let me write out what that is. So equivalently, well, we're always assuming that we're soluble. And as I said, we're always restricted to finitely generated pro-P groups. So we have finitely generated soluble, the negation, not p-adic analytic. And we want to show that the Hausdorff spectrum is infinite, contains infinitely many points. That's what we want to show, because that's easier. Easier to show this in some sense. Right, okay. So how does the proof go? So we really do zoom in on the fact that it's soluble. And what does it mean to be soluble? That just means that if you look at, it means many things, but if you look at the derived series, at some point it becomes trivial. Okay? So we're going to take advantage of that. So let me just set my notation for the derived series. So I'm going to write G round bracket 0 for G, and then G round bracket J is going to be the commutator subgroup of the minus 1. This is my notation. Okay, so we know that at some point for J large enough, we have the trivial subgroup, and we know that the trivial subgroup has 0 Hausdorff dimension, and we know that G has maximum Hausdorff dimension 1. So in other words, if we start at the, I want to write it the other way, at the first term, the 0th term in some sense here, we've got Hausdorff dimension 1. And then if you keep progressing along, at some point, you are going to get Hausdorff dimension, for J large enough, you're going to get Hausdorff dimension 0, for J large enough. This just comes from it being soluble. So the key thing is, when does it go from 1 to being below 1? So we know that we can find a maximum K, non-negative maximal, such that you're at the last point where you have Hausdorff dimension 1. Maximal such that the Hausdorff dimension of the kth derived term is 1. And after that, it's below. Okay, so we're going to utilize this fact. How? So remember, what are we trying to show? We want to show that the Hausdorff spectrum is infinite. This is what we want to show. And there's one tool out there that we've used quite a bit, is to show under certain nice conditions, so 2 nice settings, we can show that the Hausdorff spectrum contains an interval, so it's very infinite. So this tool requires, so we're going to need an injection of a tool here, and the tool requires 2 things. So you have to have a happy subgroup. So the formula for Hausdorff dimension, which I just erased, remember there was a lower limit in the formula. So if you can find a subgroup that its Hausdorff dimension is given by a proper limit, so the same fraction over here, the same log of the respective index over, so the same formula we had here, but if it's given by a proper limit and not a lower limit, that's one thing that we need. And then the second thing, which I won't write out, I'll just tell you, we need that every finite, so we want H to not be finitely generated, should be infinitely generated. Yes, and we want that every finitely generated subgroup of H. So if we look at finitely generated subgroups in H, we want the Hausdorff dimension of all of these guys to be bounded well away from the Hausdorff dimension of H. If I call the Hausdorff dimension of H psi, then you know how to write this down by saying bounded away there exists some epsilon such that the Hausdorff dimension of all these k's is epsilon away from the psi. When you have those nice conditions, you can construct an interval. I won't say how, it's not difficult, but you kind of construct lots of infinitely generated subgroups that fills in the gap between psi and the epsilon away from psi. So the happy subgroup that we're going to take here in order to apply the tool is this g to the k. And we are going to use the fact in order to show that we've got the Hausdorff dimension of all finite generated subgroups bounded well away from that of H is to use the fact that this quotient is abelian. Actually, it's enough that it's p-adic analytic. And here, in order to get that you've got all finitely generated subgroups having Hausdorff dimension bounded well away from that of H, you bring in the fact that using this is where you use, so abelian is always p-adic analytic. So this is where the structure of a p-adic analytic group, so I'm not going into any detail, comes in. And as I said, p-adic analytic groups are roughly or quite abelian. This structure is very rigid, and you can then get that nice condition here. And that then gives you the interval done. And I think I'll stop here. So thank you very much. Yes, especially when you're working with, so that's in Iftach Barnea and Barnea-Shaler's paper as well, and also Michael Erschoff has used this as well. So especially if you're working with groups like this, maybe not this exactly, but these kind of groups, then you can go into the Lie algebra version, and then I think it's just the dimension of the, so not always, but the quick answer is yes sometimes, but it may not be kind of perfectly, okay, so I think I'm not too up to date with it, but it could be that the Hausdorff dimension, you can write it in terms of the Lie ring dimension over the dimension of the Lie ring, but you can't always go, I think, the other way. So if you look at the quotients of those Lie ring dimensions, it may not be the Hausdorff dimension. But yeah, people have used that quite a bit, yeah. So are you saying that this is 0? The Hausdorff dimension of this is 0? Is that this little k? Oh, sorry, the Hausdorff dimension of this. Yes, as long as it's strictly less than 1, so it can be 0, but that's fine. Then that's okay, then k is 1. Whenever it happens at some point, but it doesn't matter where it happens. Yes. Yeah, we allow 0. Yes, so one thing I skipped, so they actually had an in-between result. So if it's p-adic analytic, we know exactly, well, there's a nice formula, so there's a long equals. The Hausdorff, okay, well, let me start again. So if G is p-adic analytic, and then if you look at this closed subgroup, then the Hausdorff dimension of H in G is equal to the dimension of H as a Lie group over the dimension of G. So it may not be all of this, but yeah, we're definitely within this.